So, welcome to this next lecture, and then here is when we would be going down as a continuation of what we had done in the earlier one with introduction to deep neural networks, and as I said in the earlier class that we would be discussing on to the history of deep learning with neural networks as it has been evolving. So, this is more of centered around the theme of family history of deep learning and how these deep neural networks have been going around over there. So, if you look into the origin and growth of these networks, so as we had also done like been discussing for quite some time, and so what these neural networks over here essentially are that they are not something new, although deep learning as such has come to a limelight in just the recent past within even less than half a decade as of now, but then neural networks have been there for quite a long time. And as we say that say somewhere around 1950s is what is called as the age of these neural networks, and this is when the mathematical definition of a neural network and the basic perceptron as we see and what we had studied in the last week's lecture was about. So, this mathematical model was what was proposed just around the ages of 1950s, and then eventually what it led down was from a very simple model of McCulloch and Pitts of neural network in 1943 to the unsupervised way of learning following down a Hebbian rule, and then going down to supervised learning with the Rosenblatt's perceptron in 1958, and then eventually after a lot of delay in from 1980 by Palm and then Hopfield in 1982 was the associative memory concept, and these are what lay down as precursors to what deep learning is today based on. So, around in the time of 1960s there were some more interesting things which started happening. So, initially till around the era of 1950s what was going on is that the mathematicians were independently working, and then they were not at all there was not much of an interdisciplinary interaction going on between different fields over there. Now, around in 1960 there started to be these interdisciplinary collaborations between mathematicians who were working out on developing out neural networks and neuroscientists. So, this is the first time when you could see electrical engineers, people of mathematics, information theory, and then also neuroscience researchers coming down into together, and the whole objective was, can you find out whether this whole mathematical model of a neural network has some sort of an analogy or does provide a plausible explanation of how biological neurons within say the human body or within living organism, any kind of a living organism does have the neural network and the neurotransmission pathway. So, whether it boils down to the same sort of a neurotransmission pathway over there in another living organism. So, that is what was going down in 1960. So, the first one was by Hubel and Wiesel, and what this gives down is the visuosensory cells which respond down to edges, and then what they found out eventually had a very interesting culmination, because when we get down into those initial neural networks and trying to do down with digits recognition, you would find out that the first few layers or the first few hidden layers over there, they would be what are responsive to more of edges and complex patterns of edges. And in fact, these discoveries of 1960s did help us find that within our biological neurons, within our vision system from our eyes, the first few things which we recognize are basically edges, line like behavior. So, straight lines, curved lines, or say circular arcs, these are the ones which are the first level of behavioral recognition which happens in order to make us recognize a particular object and then associate it to classifying it out. So, the next one was feed forward multilayer perceptron, and then that is the standard multilayer perceptron which we are looking over here and which we had studied. So, in the subsequent lecture we would be going down to mathematical depths into them. Then around 1960s is came down what is called as a neocognition, and these were the first theories which were being proposed on with this kind of an association with neuroscientists in terms of understanding whole images. So, what they found out is apparently it turns out that these neural networks, as we were initially thinking, are fully connected structures, but then within the biological system or within our bodies they are not fully connected, but they are sort of like what is called as a convolutional. So, instead of, so if you remember clearly in the first week's lecture on neural network where I was writing down the mathematical model. So, you had a x into w. So, there is a each is a unique weight which is associated with one neuron and associates to the other neuron. Whereas what it comes down from this neocognition perspective is that these weights over here are not a huge family of weights. So, each neuron does not have a unique weight, but it is basically a combination of weights which has a translational property. So, that would mean that you can operate these with a convolutional kind of operator. So, X is convolved with a weight matrix called as W, and the resultant is the convolutional sum of this coming out over there. Then we got down into something called as a weight replication, which is across. So, if my left eye has a certain sort of weight, my right eye will also have a replica of those weights. This is what it came down, and as we go into more understanding of these deeper networks, we would find out that weight replication within these kind of stereo networks or pairwise networks is again a common thing, which either you impose it implicitly, or even if you do not impose it implicitly, it would turn out that they would learn down directly, naturally using our learning rules. Now, from there went on to this new discovery of what is called as a max pooling, and was a very important concept as far as convolutional neural networks within deep architectures as of today go down. Then came down this idea of backpropagation or the learning rule. So, what we were doing down yesterday was that gradient descent over there, but then with that gradient descent, so you remember that we did take a derivative of the cost function with respect to the weights of the network. Now, when we try to solve this whole derivative over there, you would see that there would be something for a multilayer perceptron that it will be going down across the different depth layers. So, from the final target output layer via the immediately next hidden layer to the next hidden layer, and eventually coming down to the input layer itself. And as this whole progresses along the depth from output to the input, that is why it is called as a backpropagation. So, we will come down to the mathematics and more details of it in the subsequent layer. So, this is where the history was, that this crucial learning rule on which whole of deep learning resides today is a discovery which was from 1985, and that is almost close to 30 years as of now. So, going down from there is more things which came down in 1980s to 2000, and this was a point where we had even more complicated problems. So, one of them was what is called as the recurrent neural network, which started coming down around the 1980s to 2000. Then came down the local learning within feed forward neural networks, then advanced gradient descents, then sequential network construction, which is quite critical, because what happens is that when you have a complex problem to solve, you would not like to solve it from start to end, but then go down by a certain route and then keep on solving it out one at a time. So, it is like breaking down a bigger complex problem into through multiple number of smaller problems over there. Then came down unsupervised pre-training, or what we would also be knowing as autoencoders subsequently, and then as we go down in the next few lectures. So, we will be initially starting with going from a multi-layer perceptron onto an autoencoder, and then understanding what is the relationship between a multi-layer perceptron and an autoencoder, and then that is what will be going down through backpropagating convolutional neural networks as well. So, these very simple models are what construct down the basic building blocks of understanding a very deep neural network, and they were all which took place in 1980s to 2000s. From there, at the start of this particular millennium in 2000 is what is more of heralded as the era of deep learning, because all the theories which was developed before 2000 is where you needed a lot of compute power, and then around this time is when this compute power, software libraries, implementations and data sets, and then you definitely need a huge amount of data as well. So, these data sets and everything is what started coming down, and eventually around in 2000 we had enough of consumer grade compute power to get these working. So, this too much of mathematics to be made it solvable within a human lifetime. So, today if you solve a deep neural network, you can pretty much train a very complex model on challenges like ImageNet or something within 1 to 2 days, or maybe maximum of a week within your computers what are within your reach. Whereas, if you look at the era of early 2000, this would have taken more than a month's time, or some of these problems were even what required training for over a year, and that was not feasible engineering in any way. I mean, very few people had resources to spare enough for this one, and that is one of the prime reasons why deep learning was still out of the reach of a lot of people, and was not coming into the consumer space. So, from there In 2006, some interesting things which happened was this advent of the GPUs, and with NVIDIA and a lot of other partners strategically positioning their business around from just mere computer graphics generation or some of this mesh grid like solvers for multiphysics or physical simulations, to getting down more of a compute centric thing, and getting down architectures of memory, interfacing, data transfers, which are something which are analogous to support down this high bandwidth requirement within neural networks for their implementation for data transfers. Because if you clearly see, I have one layer and then via certain number of weights I connect it to the other layer. So each of these layers are what require certain memory. The weights over here will also require certain memory, and this operation, in order for it to happen, it will require a lot of memory transfer. So whenever I do a x into w, I would x1 into w1, so there are two memory fetch operations and then a product and then write to a memory. So for every one single operation there are 3 memory operations of read write which are going down over there, and this is from a very heavy volume RAM. So basically your CPU to RAM access bandwidths need to be really higher, and then these getting better and better is what led down to the advent as of now. So from there on 2009 was a GPU implementation of deep belief network, and which was very crucial in terms of being able to get down these belief networks working down. And then in 2011 came down the max pooling CNNs on the GPU, and this was with advent of certain critical architectures within the hardware itself that it led to much faster. Otherwise earlier max poolings were things which had to be done only on the CPU side of it. So as we get down more into details, you will get down where these libraries accelerate and what are the hardware constructs which can be addressed and referenced down by the software libraries directly for the best access. And then in 2012 was the ImageNet winning model by Alexander Kripke, AlexNet of 2012, which is the one which, so this was the first deep learning model which was beating down any of the classical models for winning the ImageNet challenge, which recently closed down in 2017 and then got remodeled into others. So this is more of the history, and in the subsequent classes we would be touching down on one single attribute of this history, one single model, and then see how this has contributed in a big way to what we see deep learning as of today. So as we have gone down through the history, the next which comes down is a family of these deep neural networks. Now these deep neural networks can typically be divided into 3 families as we call them. So one of them is the fully connected networks. Within this fully connected networks comes down the concept of autoencoders, and so there can be autoencoders, stacked autoencoders, sparse, denoising, as well as convolutional. So convolutional autoencoder is some sort of a relationship, some sort of a hybrid between a convolutional network and the autoencoder itself. So what autoencoders do is typically what we will be studying in a subsequent, but to give you a very gist of it. So if I have a pattern X, I would somehow encode it through certain weights in order to get down the same pattern X as the output. Now essentially you would see that well it does turn out what is the use of all of this, like whatever I put down in the input I get the same as the output, but you see there are multiple uses of it. One is you can do a denoising out of it. So if I have a noisy input side over here, somehow I make this network so that it gives me a noise free, so you can use it as a cleaning image cleaning filter, a denoising option. You can use it in order to find out a latent representation, a compressed version of whatever is given on the input. So if my hidden layers keep on getting smaller and smaller than my input layer or my output layer, so somewhere in between what I can do is, if my input is some 1000 neurons, I can get down a hidden layer of 100 neurons, and if I am able to through this network get down 1000 neurons again back, so it means that I can compress down 1000 pixels to 100 pixels. So this is an image compression which it can solve out. So we will come down to those examples as well of how to get down an image compression as well running down with these neural networks. Then the next one is what is called as a belief network. So the typical one is a restricted Boltzmann machine, which is already known quite widely within the community. So this is where you have some sort of a Boltzmann distribution being carried down. So, if I have an input and an output are connected via a hidden layer, and this hidden layer is say which produces outputs of Boltzmann distributed. So, any variable state of this hidden layer is a Boltzmann distributed variable. So, given any input you can get an output, or given, so and input outputs are not so predefined over here, it is just a pair of x and y. So, if you give a y, it can also give you an x, given that the hidden layer over here is Boltzmann distributed. And then when you stack them one on top of the other, that is what leads to something called as a deep belief network. So, this is where all inputs, all outputs and all intermittents are directly connected. When you change all of these direct connections or a dot product like connection to a convolutional like connection, and then that would necessarily help you to get down a space invariance, because now you can have non-locality as well addressed down. Then these kind of networks are what is called as convolutional networks, and or again also briefly termed as convnets. So, today what you would hear down as say GoogleNet, AlexNets, LayNets, UNets, then DenseNet, residual networks, ResNets, these are all what rely predominantly on the first few operational layers in terms of convolutions itself, and are typically defined as convolutional networks. From there comes down the next version, which is time sort of a neural network which operates on the time space itself. So, and it is also called as a recurrent neural network. So, what happens is that the output of the neuron gets added down to the input of the neuron in the next time step. So, not in the same time step. So, if I am processing down a sequence, so the first time stepping whatever is the output, that output will be getting down to, when I am trying to process down the next in the time sequence data over there. So, this is very useful for doing so natural language processing, so where say you want to do an error correction measure. So, you would see that often when you are typing on your smartphones, if you just start typing a message, after one alphabet it starts showing you a few alphabets or even words over there, and as you keep on typing more alphabets, it keeps on getting better and better, and you see closer to the exact word. Okay. So, these are kind of things which are associated with recurrent neural network behavior. So, we will be getting down more and more details into of them, but while we will not be doing this say sentence or word correction kind of behavior, we would be exactly using these recurrent neural networks for our video analytics problem, where it's frames which are not so distinctly different, but somewhat related, but come down at in a series sequence of time, and then can we use some sort of a recurrence property between their object appearance across different frames as in a video in order to get down an analysis of a video or classify a video. So, that is broadly the three families in which they are. And today if you see, so this deep learning thing is no more sort of a science fiction which it was initially thought of to be. So, you can get down to these very interesting examples on, so NP contemplation is just a website over there, just Google it and find it out. So, what it does is that if you see over there, those black and white dots over there are basically some neuron outputs of a restricted Boltzmann machine. So, as it generates a Boltzmann distributed 0 or 1 0 or 1 kind of a output over there. So, this is a perfect black body's output, and you would get down a face corresponding to it. So, it's a bit creepy, because just by doing certain black and white or zeros and 1 sequences over there, you can generate a whole human face looking down, and every time it does generate a different face coming down. The other is a paper where given a face, you can use these kind of deep neural networks in order to synthesize different facial expressions. So, as we go down into more of regression modeling on deeper lectures and in the next courses in the subsequent weeks, which would be a bit later on, we would be coming closer and closer to how to even synthesize these kind of images using some simple black and white dots as well. So, from there going on to application side of it, where we stand today is say Facebook's face recognition or object recognition. Whenever you upload an image, it just says whether these people are present over there or whether it's you or not. So, that's what has been building up on top of the years of corpus you have built by tagging your individual faces. So, in the initial days, if you remember, so that's like almost close to a decade back when Facebook was starting up early. So, you could put down images and then you could draw a square box around those images and then tag down your faces or your friends over there, and that was helping them create a large corpus. And eventually, initially those boxes were all fixed size square boxes, Eventually they got into variable sized but square boxes, then it got down into rectangular irregular shaped boxes, and then not necessarily a square aspect ratio box coming down. Then you could annotate objects then, and that's what helped down in creating a lot of corpus of this supervised learning coming up. So eventually from there, Baidu is a large search engine within China, and this is where deep learning powers its retrieval engine. So if you put down an image of a person, it fetches you all possible images of the person and does not restrict only to photographs. So there can be even hand sketched versions, as you see in the last row over there. There can be person who is tilting the head and on some different poses, and which is a really interesting part, because if you put down some object or a person's face, you would like to get down that person's all other faces over there. So this is a very critical search task which this particular kind of technology of deep learning is helping us achieve in a real time scenario. Then there is this particular website on Cortica, which what it does is that it pulls down random stream of images from the web and then starts generating small captions over there, or more typically it's like what is present in the image, and it can give you 1 or 2 words over there. And this is what it does on the browser side. There is nothing running on the server side, it works on your browser side. And it was really fun to watch out. So more about them is with this kind of products on fashion. In fact now even some of these big e-commerce companies like Amazon also have launched it out, and that's about where you can take an image of somebody wearing a dress, and then it somehow searches and finds out through its visual catalogs and gives you the product catalog category on their e-store, and you can buy that sort of a dress. So this is where it's going down on impacting the consumer space as well. So from there you see a huge aspect of going it into self-driving cars and autonomous driving, full autonomous mobility, and not much left behind is Microsoft thing. So somewhere in 2014 they started up getting this public release on what's called as Adam, and today if you see there is Microsoft's Cortana for speech and as your assistant for PC systems. So they are like really building up huge in terms of it. It has its own libraries itself. There's something called as a Microsoft CNTK, which has a cool API where you can use that API within your websites, within your apps, anything which you are developing. And what this can do is, given an image, it can say whether it's a male, female, what's the age of the male, these kind of intuitive information, and also give down even from spatial expression to give down expression analysis, whether the person is angry or some sort of emotional dependence, whether he is happy, he is smiling, these kind of things. So this is what is becoming increasingly deep learning powered AI as of today, and that's where it's going. But the challenge with this is even bigger, and that's where we are almost at the end node. So as Trishul Chilimbi had put it down, was an interesting observation, was that this whole thing of deep learning is quite like quantum physics at the beginning of the 20th century. And the reason behind this was more of this, that experimentally and based on practitioners and software coders, these experiments have been far ahead of its time, because we are getting down more results, better results coming down. But the problem is that there is another group of people who are theoreticians and who come down to this aspect of explainable AI, which is drawing an explanation as to why is this particular model working, and that's something which we are still not at a point to understand heavily. We know some of these explanations, but not all of these explanations, and that's a prime research, which is the major challenge within deep learning and learning with deep neural networks as of today. So as we go down through this lectures, while I will be covering a substantial part of what works, I will also be working down on why it works and what are possible explanations of why these particular deep neural networks can do, and expecting that you can also build up newer architectures on your own side by going through this whole route. Or if you have a different kind of a candidate search, which is you have some n different numbers, say 3 or 4 different architectures, then how can you choose out which is the architecture which is most suited to solve a particular problem in hand. And that's what we will be doing from theory to experiments, and eventually that's the whole objective of this course itself. So finally, as we come to an end, I have a few take home messages for you. So one is, you do require hardware resources, and what you can do is get down any of these and which are really good. Except for, let's say, custom workstations, you would need some sort of GPUs to build up, and in India it's easier to get down a GTX 1080 Ti or a GTX 1060 and from NVIDIA, and then this can help you create down a machine. So eventually, so we have one session in which we would be unwrapping and unboxing a machine and show you different parts so that you can get a hardware set your place, while we also have done the clustered access given down for participants of this course, so that you can get down access to an HPC. So or you can obviously buy down this say DGX1 dev box from NVIDIA, which does come at a quite premium price, maybe just for a few institutional purchases, but not for much of personal things. Then on the toolboxes, all of these are open source as of now, so you can use any of this other than the one on MATLAB, for which you will definitely have to pay for the licenses. But the MATLAB neural network toolbox since 2016 does support autoencoders and convolutional neural networks as well. So if you want to read more about it, go through this website on deep learning book, which is now also available as a printed book itself from MIT Press. You can get this book, and that's what we will be using as a major reading material over here. Other than, and whenever there is something else, I would be putting down pointers to those exact materials. And to follow down on conferences, it's NIPS and ICLR, which form down the major corpus of what we provide today and disseminate in terms of newer research in the field of deep learning. So with that, we come to an end of this particular lecture on the introduction to deep learning. So in the next class, I would be getting down started on what will be the toolboxes and toolkits of how to get started, and eventually we will get down into writing down the main math of a multi-layer perceptron and getting into an autoencoder, and then subsequently going into coding exercises for autoencoders as well. So with that, this comes to an end, and thanks.